Hello everyone and welcome back to Calculus. In today's part 36, I want to introduce the power of polynomials combined with calculus, specifically the Maclaurin series, otherwise known as the Maclaurin polynomials. However, before we get into that, first I want to thank all the nice people that support me and this channel by liking and subscribing. As a thank you, I post all PDF versions of our lessons in the description for you to download and look at for free. Now, continuing with today's topic, in mathematics, polynomials are like the Swiss Army knife, versatile, powerful, and incredibly useful. As you might know, they can be as simple as a straight line or as complex as a winding curve. But what if I told you that these polynomials, when combined with calculus, can mimic any function that you might imagine? These functions would range from the smooth waves of sine and cosine to the explosive growth of the exponential functions and everything else. All can be accurately reproduced using nothing but a series of carefully crafted polynomials. And we accomplish that with the help of the Maclaurin series. So, in order to understand what it is, I want you to consider a polynomial of degree 5. So, that would simply be given by a0 plus a1 times x plus a2 times x squared plus a3 times x3 plus a4 times x to the power of 4, and finally a5 times x to the power of 5. We'll name it capital P of x, and in this case a0, a1, a2, a3, a4, a5 are simply coefficients. At the same time, I also want you to consider a function f of x given by the natural log of 1 plus x. Now from this, we are going to continue by examining the behavior of both functions at x equals to 0. Our goal here is to make the polynomial match our function f of x as closely as possible using the help of derivatives. So first, we begin with the constant term of the polynomial, specifically a0. What we have to do is equate p of 0 to f of 0, since we're observing the behavior of the function around x equals to 0. To match them, all I have to do is plug 0 into each of them and equate them. Now plugging in 0 into the polynomial leaves me with a0, and plugging in 0 into the function leaves me the natural log of 1, which is just 0. So that means the constant term of the polynomial is 0. In other words, it does not exist. There is no constant term. Next, let's take the first derivative of both the function and also find the first derivative of our polynomial. For the function, the derivative of the natural log of 1 plus x is simply 1 over 1 plus x. For the polynomial, the a0 vanishes, and what we have left is a1 plus 2 times a2x plus 3 times a3x, and so on. And once again, in order to match the polynomial to our function, what I have to do is plug in 0 into the derivative of the function and plug in 0 into the derivative of the polynomial and equate them to each other to find the value of a1. Now f prime of 0 is just 1, and after we plug in 0 into the derivative of our polynomial, what we get is simply a1. So that means a1 is equal to 1. And I will keep repeating this process. Now I find the second derivative of our function and the second derivative of our polynomial. And then I plug in 0 into each of the second derivative, equate them to each other in order to find the solution to a2. And what we get is that a2 is equal to negative 1/2. And we can keep doing this until we find a5. Here I have found the third derivatives. Then I can just plug in 0 once again into them, equate them to each other to find a3. And a3 is 1/3. Please note that for the fourth derivative, we don't use 4 primes anymore. In the superscript, we simply write 4 in parentheses to denote the fourth derivative. For a4, I get negative 1/4. And finally, let's do the same thing for the fifth derivative. And finally, for a5, I get 1/5. So now that we have found all 6 coefficients, we can substitute them back into this general polynomial. And this right here would be the Maclaurin series of degree 5 for our function ln of 1 plus x. We can simplify this a bit more and write it in a more compact way as x minus x squared over 2 plus x cubed over 3 minus x fourth over 4 and plus x to the power of 5 over 5. Another possible notation we could write is mf of x, which is the Maclaurin series for the f function, which originally we know the f function was ln of 1 plus x. To understand the power of the Maclaurin series, let's take a look at a visualization of the function ln 1 plus x. I can tell you, or you can also find out yourself with graphing calculator such as Desmos or your actual calculator. The natural log of 1 plus x is this red function right here. And now if you were to plug in this Maclaurin series polynomial that we got into the function, into the graphing calculator, what you would get is this blue function right here. And you can see that in this part right here, these two functions coincide graphically. This is because the polynomial is trying to mimic the behavior of the actual f of x centered at the point x equals to 0. Hence, I mentioned in the beginning that the Maclaurin series can mimic any function that you could possibly imagine. However, before we get into the actual formula, I want to go back a little. Because the coefficients that we got here, 1/5, 1/4, 1/3, negative 1/2, 1, they were all simplified. What if I did not simplify them? Well, a0 would remain 0, a1 would remain 1, a2 would still be negative 1/2. However, a3 without simplification would be 2/6. a4 without simplification would be negative 6/24, and a5 without simplification would be 24 divided by 120. Now, why is this important? Because using this, we can write a general formula for the coefficient of an. What we do every single time is we use the nth derivative of the function evaluated at x equals to 0, and then we divide it not just by n, but by n factorial. Please note the pattern here. a1 was just 1, then it became 2, and then it jumped all the way to 6. Well, the only possible pattern that can give us these big jumps from 2 to 6, from 6 to 24, and from 24 to 120 are factorials. Because we know 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, and 5 factorial is 120. Hence, an can technically be expressed in this format. However, there is one thing we have to compensate, it's the negative sign. We have an alternating polynomial, meaning negative 1 would be raised to the power of n plus 1 to give the alternating effect, plus minus, and so on. And hence, after so much hard work, let's finally write the definition of the Maclaurin polynomial. If we have a function f of x which can be derived n times at the point x equals to 0, then the Maclaurin series, usually denoted by the capital P of x or also as m with an index f of x of degree n for the function centered at x equals to 0. In this case, that would be given by the following. P of x is going to be equal to f of 0 plus the first derivative evaluated at 0 divided by 1, and of course times x, plus the second derivative evaluated at 0 divided by 2 factorial times x squared, plus the third derivative evaluated at 0 divided by 3 factorial times x to the power of 3, and so on. Now, there is a way to write this in a more compact way using the sigma notation. Mainly, we can say that n equals to 0, and up there it goes all the way until k, where k is just an arbitrary number, or for the better, we could use the sign infinity. And that would be of f n's derivative evaluated at 0 divided by n factorial times x raised to the power of n. Please note in the visualization, here you might argue that the polynomial is not that accurate. However, within this range, it is extremely accurate. Here we only did 5 terms. If you don't believe me, in the graphing calculator, try to plug in 10 terms of the polynomial. The graph that you're going to get is going to look something like this, which already has a greater range of accuracy than the blue function. So it means if you were to construct a polynomial with infinite amount of terms with the use of the Maclaurin series, you could accurately mimic the behavior of our function f of x. Another fact that I can tell you is that if you are wondering whether we can only build polynomials to mimic the behavior of a function around x equals to 0, you'd be partially right but also partially wrong. Because using the Maclaurin series, we can only evaluate at x equals to 0. However, the Maclaurin series is a simplified version of the Taylor series, which is something we can use to mimic the behavior of any function at any given x value. However, the Taylor series is much more complex, and perhaps that should be something for a future video. For now, this is it for today, and in the next and also the last video of the calculus series, I will show you examples and common Maclaurin series, which would be great to keep in mind. So I really hope to see you there, and have a nice day. Bye!